Well, today we're going to be talking about scientific evaluation and scientific adaptive management. These are very similar approaches where we look at trying to apply essentially the essence of science to either running a project or evaluating a project that's underway or been completed. So remember, science, the way we're going to use science is that it collects information that can be independently verified, that it uses rigorous methods for measurement, and that those measurements are rigorous. They're considered rigorous because they can be tested. And finally, it creates new knowledge that's usable. So those three things are really the essence of science. And what we're going to be looking at first is scientific adaptive management. That is an approach to being involved with improving the environment. And then the second, we're going to be looking at scientific evaluation. So in this part one, we're just going to be dealing with scientific adaptive management. So first of all, scientific adaptive management is one of the approaches, and it works well when you have low knowledge. That means high uncertainty. You have a good degree of control, and you have value alignment. We're going to see in a little bit that this value alignment is different for these large projects. It really means you have political support. But you have uncertainty, and then you have the finances and the political backing to actually undertake a large project, and you have some support. So back to the original problem typology that we started the course out with, we saw that when you have uncertainty and value conflict, you end up with a wicked problem. And with a wicked problem, you're never really finished solving it. You just have iterations and improvement. And this is where scientific management is really good. You have the uncertainty is scientific management. You have high control, and you apply that to a wicked problem. You're never going to reach a solution. That's not the goal. But you're going to continually improve the situation, and at the same time, you're going to decrease the uncertainty. That means learn about the environment that you're trying to manage. So this is really sort of the biggest hammer we have in the toolbox, so to speak, for large projects to approach them with this scientific adaptive management approach. So scientific management and scientific evaluation are very similar. And again, to review, science means evidence-based, rigorous methodology creates knowledge. And you can see that both of these topics we're going to talk about today include dealing with values. And we're going to deal with those in objective ways, like we've done before. But I want to go through and illustrate that, because that's one of the really sort of underlying themes of this course, is that we need to be able to deal with values. And a place this comes up in conflict is, what's the role of scientists in making environmental decisions that include values? So I want to point this out first, that environmental action is not environmental activism. So we're talking about taking actions to solve environmental problems. That's different than environmentalism or environmental activism, which would be the belief that you need to take action. So those two may align or they may not align. But really there is a difference, meaning in an individual, maybe an environmentalist and an environmental scientist. So, but activism, just the belief that you have to take action, is not science. So let's look at this spectrum of involvement of individual scientists. First, there's at one extreme, where it's very objective, is that the science is done by, the science is completed and the information is passed over to a decision maker, policy maker, and there's a sort of arm's length transaction. The scientists themselves just do objective science, find the facts, pass them over, then the policymaker deals with the value side of it. So this is, for example, my colleagues in USGS, this is what they do. They provide the best possible information, best possible data for their clients, and then the clients are policymakers and managers that have to use that information. Okay, another alternative is where the scientists they create science-based models that provide good options. And this is called the broker of honest alternatives. So the honest means that the values have been exposed and are actually part of the model. So there's a value dimension entailed and daylighted for each choice, and that then you would say provide a model or a set of scenarios that includes values that would be constructed. All the assumptions could be checked, and then that would go to the policymaker and decision makers. The next level up is where the scientist involved acts as a consultant. And we can see this in this description of post-normal science, which is when you have situations where there's low decision stakes and low uncertainty, you can use applied science, sort of an engineering approach. I mean, you know that it's going to work. It's an application of what you know. And at the extreme, when you have there's a lot at stake and there's high uncertainty, there's what we're going to call post-normal science, where the investigator themselves has to be involved in making the decision and value judgments because no one else is really close enough to the problem. We're going to come back to that in a second. Right now we're talking about this professional consultancy level in which, sort of intermediate in decision and uncertainty, and it really means you're paying a scientist to make a judgment. You say, collect all the information, and then we're going to pay you as a consultant to make a decision. So in this case, the scientist collects the information and helps make the decision, but often they're being paid for, as a consultant. Okay, now if we go back to this list here, we have the next level is for scientists is to be idealistic about science and pragmatic about politics. This is what Lee talks about in his treatment of Columbia Basin scientific adaptive management, and that is to really be involved in the political negotiations to get the resources necessary to do the right science. And so that political negotiations are value laden, but to separate that from the science, be very ethical about science and be very pragmatic to get the resources you need. Okay, the next level along that continuum, really these next two things, is more post-normal science we saw in the diagram before, and what Norton says is those nearest to the problem need to help make decisions. That is, they're not the only ones, but because they know the most about the situation, they should be in on the decision making. And this is where I find myself in my personal work, working in Upper Klamath Lake, is that there's some stuff that because I've been out on the lake a lot, or because other fish and wildlife scientists have been out on the lake a lot, they really know a lot about how that lake works, and they know about the values that are entailed in both in different operational scenarios. And so to ask them directly what they feel about it is also, there's the science part, here's the facts, and then the values. Those are mixed together, and you have to take the stance of an ethical scientist and be clear about what your values are and state what you think the facts show, and then what decision would come from both of those. And then finally, there's the activist, just meaning clear on the other end that there's a belief that you need to take action for some reason. You see something wrong, and without any real sort of scientific backing, or maybe even at worst the misrepresentation of science as a justification to do that. And finally, just to remind you that there's nothing wrong with environmentalism. It's just I'm trying to distinguish here between being an environmentalist, a belief system, and environmental science. And there's quite a continuum of how ethical scientists may be involved in everything from facts all the way to values decisions. Okay, now I just want to make a comment about how environmental projects are dealt with research. Now, in the university community, we have teaching, research, and scholarly community outreach. And in some areas, say for example, pharmacology, creating a new medicine that might treat some disease, we have research and graduate programs, and then that goes out through some more commercialization process into the global public good, and this might be a product that eventually goes out there. Now you need a lot of smart people all along the way to make this work, but the net gain, the net outcome is a product that really works out in the environment. And whereas in environmental work and in entrepreneurship that we talked about before and management, what we're really trying to do is have more people out there making this decision. So the product, if you will, are well educated and trained managers at all levels, policymakers, government officials. All of that is really sort of the product. It's not like we're trying to create a pill to fix something or one particular program, computer program that fixes everything. Is that we're trying to have a broad education. So it's a very different path from the research and graduate program out to implementing this environmental improvements versus, say, pharmacological or computer science or these other types of science. All right, let's talk about scientific adaptive management specifically. And first of all, the definition of scientific adaptive management is that you conduct management as experiments, and each management activity has the dual goals of fixing something that's wrong in the current environment, mitigating some problem, and understanding that better. That is, decreasing the uncertainty for future management. And given that most of these that we're dealing with are wicked problems, you're never really going to solve the problem. You're not trying to solve a problem. You're trying to find a process that will continue to adapt as the problem changes. And remember, with a wicked problem, as the problem changes, the values change. So a good case of this is in Poland when they cleaned up the communities. People then even wanted more cleaner communities and more parks. So it wasn't just cleaning it up. The values of the people changed as they saw the possibility to have cleaner air and park spaces. Okay, now to really make this very clear, scientific adaptive management is not trial and error. You're not trying to find one solution and then just try something else if it doesn't work, because you're trying to design a set of manipulations, design a set of a sequence, if you would, of management that will help you learn about the system as it helps solve the problem or work toward bettering the problem, really. So it's not just trial and error. It's not just, I'm going to go do that, and if that doesn't work, I'll try something else. That's trial and error. Scientific adaptive management is, I'm going to do this management process because it will help me understand how the lake works or how the forest works. And then because of that, I'll be able to make better decisions in the future. That's really what it's centered around. Now, there's 3 tenets of scientific adaptive management. This is according to Brian Norton. And the first is experimentalism. That is, you need to have evidence for every choice you make. You need to get that evidence from direct measurement or experience. And you can't use pre-experiential ideas and bring those in. That is, you can't have some ideology about how you think the system works and impose that. That's not scientific adaptive management. The other thing is you need to be able to address things across scales, from small scale manipulations to large scale projects. And this is very difficult because we have this problem with cause and effect issues where small, you might have one cause at a small parcel, and in the same thing on a larger landscape has a totally different effect. So this is a problem with complex, holistic approaches to solving problems. And finally, every place is unique. We have a place sensitivity. Places should be considered the environment and the human activities that take place there. So you have to really be looking at the uniqueness of the situation. And it's these 3 tenets of SAM here that also have made me choose that as a scientist I have to be involved in the decision making and help support that decision making, because experimentalism, I'm the one collecting the evidence. I know something about this. Multiscalar, I study the system at small and large. I have a good feel for this. And then the place sensitivity, I've studied different lakes. I know how each one is unique. And again, I have a much better feel for how all these play out. So it's not that I'm I am the decision maker, but I should take a role, I feel, I should take a role in letting my values be known in a clear and clear and ethical way, so people can say, oh yeah, well here, based on the information that John has, he made these sorts of decisions and he made these value decisions. See, that could help be a guide for other managers and policymakers. Okay, now we're going to talk about a major challenge to all sorts of environmental management, and that is thresholds. And scientific adaptive management helps deal with these thresholds because the goal is to try to decrease the uncertainty. So a threshold is this situation where, as we increase the stress level, then we get to a point where there's a threshold and then there's a big impact. And there's a lot of uncertainty as to where this threshold kicks in, where it starts taking off and you get a lot of negative response. And in this particular drawing I've shown you, it's an example of a multi-stable state. It's resilient around this lower stress, but it's also resilient around this upper stress in a degraded environment, and you're going to see this in the videos. Well, one way to address this threshold thing is to do management activities that are right in this range. But what if you do one that's just too far? That is, maybe you designed an experiment that didn't remove enough phosphorus from a lake, or burnt a little too much of the forest, and then all of a sudden there's a big change in the environment, negative change. Well, that's the risk we're taking around this uncertainty, and those management activities have to be carefully designed to be probing at what this threshold is without going over it. So one way to do that might be having smaller experiments, and we saw this before when we talked about management activities that took place at either short time scales or small time scales. And if those were the cases, we could choose cost-benefit analysis. But if we went over into large problems or long-term problems, we needed to use the safe minimum standard or the precautionary principle. Same idea that happens when you're near this threshold. A threshold is irreversible. Once it goes up into that other state, it can take a lot of effort to fix it back to its healthy state. So here's an example. Let's say we're trying to treat a lake, and this is supposed to be a lake. And in this little bay, we use a treatment. We use another treatment in these different treatments in all these bays, and we use that sort of an experimental way to find out. But we still don't know, will it happen on the whole lake? And also, because we use these little projects, but each one of these bays is reversible. And then when we do that, we have to be able to look at the scale. What would this treatment, if it does work in this little bay, would it work at the whole lake? And that's a problem. That's really a challenge for environmental restoration and mitigation problems. Now finally, threshold systems. It's important to understand threshold systems. So one aspect of a threshold system is just compare. This bottom one is a threshold system. The upper one is a linear system. For the linear system, every little bit of stress, we get more impact. And then similarly, every little bit of stress up here, we get more impact. It just accumulates. Whereas a threshold system, we go along for a while, and then all of a sudden there's a big increase in stress. And this stress level down here, this is a healthy and resilient system down here. And up here, this is a resilient but unhealthy. It's a negatively impacted system. And you're going to see these in the videos. This could be like a lush grassland, and this could be a dry desertification area that's been a lot of erosion. Okay, so the idea is to try to avoid this threshold. But we also see, remember, this is resilient down here, this is resilient up here. We also see this, what we call hysteresis. And that's where the forward path and the back path are different. So in this case, imagine a healthy person. And now all of a sudden there's enough stress. Person gets sick and now is in the sick and resilient state. Like it's hard to get well. You have to help the person recuperate by decreasing the stress all the way to a certain point, and then finally they get well. So they don't just, it's just like you decrease elements of the sickness until you're well. You have to actually reduce the stress quite a bit before that person gets well. And the same thing can happen in ecosystems. In order to recover from a highly weathered and eroded system to a lush grassland, you might have to take a different path and really make conditions much better than you might think they need in order for them to recover. Okay, now there's, even on top of that, there's another situation that happens quite often, which is have this hysteresis with the barrier, so that even if you do get the stress levels down low, you need some sort of intervention in order to get that to help. And this, in the human metaphor, this would be like, okay, you're sick, but now all of a sudden you really needed a heavy dose of, an overdose almost of antibiotics, or you needed some sort of surgery, or you need something like that, some intervention. You're not just going to get well on your own and then then you recover. And in these ecosystems, for example, in lakes, some of these barrier, some of these things that might have to use to overcome barrier are introducing new species of fish, or in some cases they introduced zebra mussels, which is an invasive mussel that filters out algae. In some cases they shot all the birds that were going to come in there and might poop in the lake and add nutrients. So these are interventions. And again, in the videos you're going to see these sort of interventions might be some active process that sort of kicks off the recovery. All right, well that's the sort of the part about scientific adaptive management. And there's an example here. You can click on this example and just sort of go through, lead you through an outline of the example where it talks about using a model and some of the characteristics. And that's a little too detailed to go through here right now, but it'd be useful for you to go through that.